Good morning, professors. I am Ashish Rekhani, and me, along with my friends Anushka Srivastava, Vibhu, and Deepiha, will be presenting on the use of AI and deep learning to solve the traveling salesman problem. In this presentation, we will be covering the use of the Transformer network to solve this particular problem. This presentation is inspired and based on the research paper titled The Transformer Network for the Traveling Salesman Problem by Professors Xavier Bresson and Thomas Laurent. Let's begin. First of all, let's understand what the traveling salesman problem is. Given a list of cities and the distance between every pair of cities, the problem is to find the shortest possible route that visits every city exactly once and returns to the starting point. This problem was first formulated by William Hamilton, and it's a very famous NP-hard problem, meaning there is no polynomial time known solution for this problem. But why is this problem so important? The traveling salesman problem, or TSP, actually belongs to the larger class of routing problems which are used every day in industries like warehouse management, transportation, supply chain hardware design, manufacturing, and so on. Slightly modified, it appears as a subproblem in many areas such as DNA sequencing. It also appears in astronomy, as astronomers observing many sources will want to minimize the time spent moving the telescope between the sources. In such problems, the TSP can be embedded inside an optimal control problem. Let's consider the example shown on the slide. Given this particular graph, the shortest possible Hamiltonian cycle, which is a cycle which visits the start node and visits every other node exactly once. So in this given graph, the shortest route is visiting starting from the node A, we move on to node B, followed by nodes C, D, E, and back to A. The cost in this travel is basically 12 plus 3 plus 2, that's 17 plus 4 21 and plus 8 29, which is the minimal cost. Now, considering the importance of this problem, and since exhaustive search of all the possible paths has a complexity of n factorial, this makes it extremely difficult and also the reason for its extensively studies in optimization. This problem is used as a benchmark in optimization problems. It has led to many important discoveries and optimization techniques like cutting planes, branch and bound, local search, as well as simulated annealing. Traditionally, the combinatorial TSP belongs to a class of combinatorial problems. Combinatorial problems are the problems consist of finding an object from a finite collection that satisfies all constraints. Traditional approaches include exact algorithms and approximate or heuristic algorithms. Exact algorithms, as the name suggests, give the optimal answer and include various known algorithms and techniques like exhaustive search, dynamic programming. These algorithms, although guaranteed to find the exact solution, will become quickly intractable as the value of n increases. That is, as the number of cities increases. Second class of problems is the approximate or the heuristic algorithms. Here we trade optimality for computational efficiency or time complexity. A heuristic, that is a simple rule or an estimated guess, is designed and applied iteratively to get the solution. The complexity of such problems is polynomial, and the quality choice is dependent on the approximate ratio that characterizes the error. Now let's study about some exact algorithms for this particular problem. First of all, we have the dynamic programming approach. Secondly, we have the Gurobi, which is the general purpose integer programming solver, which also employs cutting planes and branch and bound techniques. Thirdly, we have the Concord. Concord is a highly specialized linear integer programming. Along with it is embedded cutting planes and branch and bound techniques specially designed for the traveling salesman problem. And lastly, the traveling salesman problem can also be modified or formulated as an integer linearing problem and solved therefore. Let's understand more about Concord. Concord is a problem for solving the travel salesman problem. It was first written by David Applegate, Robert Bixby, and William J. Cook in ANSI C. It's a highly specialized version of linear integer programming using cutting planes and branch and bound techniques. Concorde is widely regarded as the fastest exact TSP solver for large instances to currently exist. Overall complexity for Concorde is big O of n to the power 2.5 multiplied by B of n. O of n to the power 2.5 is for the linear programming and multiplied by O of B of n for the number of branches to be explored. Concorde's TSP solver has been used to obtain the optimal solutions to the full set of 110 TSP library instances, with the largest having as many cities as 86,000. Next, we'll be studying about approximate algorithms, and Deepiha will be explaining the same.
Okay, next we have approximate or heuristic algorithms. This includes the Christoffels algorithm, which is a heuristic-based polynomial time near-optimal algorithm with approximation based on minimum spanning tree. Next, we have insertion algorithms like farthest, nearest, or greedy algorithms in practice, among which the best one is farthest. Then we have Google OR tools, which is a highly optimized program that solves TSP by applying different heuristics such as simulated annealing, greedy descent, and etc. Then we have two-opt algorithm, where the heuristic is based on a move that replaces two edges to reduce the tool length, and similarly three edges for three-opt algorithm and LKH3 algorithm. We have the LKH3 algorithm, which is probably the best heuristic for solving TSP, and it's based on 2-opt and 3-opt with better way to select the edge candidates. Given a feasible TSP tool, which is a Hamiltonian cycle, the algorithm repeatedly performs exchanges that reduce the length of the current tool by replacing k number of edges until a tool is reached for which no exchange yields an improvement. This process may be repeated as many times from the initial tools generated in some randomized way. It generates near optimal solutions for symmetric TSPs, but some of the problems to be solved by LTH3 are best conceived as asymmetric problems, even if the costs are symmetric. Then we have the hierarchy of traditional TSP algorithms. Here we compare the approaches discussed so far. This diagram shows how the traditional approaches perform in terms of complexity, and to make the approaches feasible, we are required to compromise on the accuracy of our solution. On the rightmost, we have the naive approach of exhaustive search. This will give the optimal answer but will run in n factorial time, so it will become intraceable for n greater than 20. Similarly, the dynamic programming approach will become redundant as n exceeds 40. Next exact approach we have are the Concord and Bureau B, both of which are good only till n is in some thousands. Then time complexity decreases significantly as we leave the optimal solutions and allow some approximation with heuristic approaches like LTH3, Christoffels, and farthest insertion. Next off, we have application of deep learning in TSP. Deep learning has significantly improved computer vision, natural language processing, and speech recognition in the last decade by replacing handcrafted visual, text, and speech features by features learned from data. Therefore, we find it worthwhile to explore the application of deep learning techniques on combinatorial problems with the goal of discovering better heuristics than the ones handcrafted with decades of human research. TSP being a prevalent problem which has been researched for over 70 years makes it a good candidate to test the application of deep learning, and by its nature, developing an efficient DL solution for TSP might help develop similar deep learning based solutions for other NP-hard problems. The last 5 years have seen the emergence of promising techniques where graph neural networks have been capable of learning new combinatorial algorithms with supervised or reinforcement learning. Next, we have transformers. A transformers is a deep learning model that adopts the mechanism of self-attention, differentially weighing the significance of each part of the input data. Since its conception, the idea has been heavily used in the fields of NLP and computer vision. Like recurrent neural networks, transformers are designed to process sequential input data, such as natural language, with applications towards tasks such as translation and text summarization. However, unlike RNNs, transformers process the entire input all at once. The attention mechanism provides context for any position in the input sequence. For example, if the input data is a natural language sentence, the transformer does not have to process one word at a time. This allows for more parallelization than RNNs and therefore reduces training times. In the encoder, the input sentence is converted to a vector representation by translating each word to a vector while maintaining the context of the entire sentence using the attention mechanism. For example, meanings of words in an English sentence can change depending on the context, which is derived from the entire sentence. The decoder takes as input the vector representation formed by the encoder as well as the outputs generated by the decoder itself so far. Unlike the encoder's bidirectional self-attention, the decoder uses a unidirectional autoregressive masked self-attention, which means the inputs of one side of sequence are kept hidden from the decoder and the context is formed based only on the other side and the output so far. Thus, decoders offer great performance on prediction tasks like text generation. For example, in cases like text autocompletion, when predicting for the next word in the sentence, the decoder would have access to the representation of the English language itself formed by the encoder as well as the words input by the user and predicted by the decoder. Over to Vibhu.
So, here's the approach proposed by Preston et al. We look at the TSP as a translation problem with source being a set of 2D points and target would be to achieve a tour with minimal length depicted by a set of indices of the selected nodes. As the translation problem in NLP has made significant progress in recent years by using transformer architecture, we propose to use a similar architecture for TSP as well. We train using reinforcement learning with initial settings as those from Cole et al. As a baseline. The reward is the tour length and the baseline is simply updated if the network trained improvises it on a set of TSPs. Now, talking about the encoder part, the set of points in a 2D space that we have as source would be converted using self-attention into a representation that would make it easier for the decoder to find the shortest path. The encoder utilizes multi-head attention, residual connections, and batch normalization. A dummy node Z is also inserted as a start token. The memory and time complexity of this process is order of n square. Looking at the maths involved here, we start with h at l equals 0, which is simply a concatenation of the dummy node Z picked at random followed by the source of points. Then, at each layer of the L layers of the encoder, we update and calculate HL plus 1 to be softmax of QL multiplied by transpose of KL over the square root of D multiplied by V of L. And each of those intermediate terms can be calculated as the formula seen in the last three lines utilizing HL as an input. This process stops after a pass through all layers of the encoder and the output is H encoder. Now, moving on to the decoder, the decoding is done in an autoregressive manner one city at a time. Suppose we have decoded the first T cities in a tour and we want to predict the next city. The decoding process would have 4 steps. Part 1 would be to start with encoding the city I sub T and positional encoding. Part 2 would be to encode the Tth city and the partial to itself using self-attention. Part 3 would be to query the next city with non-visited cities using multi-attention. And finally, part 4 would involve generating the final query using a single head attention and index sampling. So, part 1. We start with encoding of the IT city. It is calculated as H dec sub T equals H ENC sub IT plus positional encoding at T, where H dec sub 0 is initialized as H ENC as the dummy node Z. Add positional encoding P to order the nodes in the tour. The positional encoding is calculated as sine 2 pi fi times t if I is even and cos 2 pi fi times t if I is odd. The decoder would have access to the cities added in the tour so far and would therefore add the ID city at its optimal position in the partial tour. This process can be seen in this graph at the bottom right. Part 2. Encoded Tth city with the cities in partial tour using self-attention. That generates the query for time t. Then multi-head attention, residual connection, and layer normalization are used in this layer. The memory and speed complexity is order of OT at each recursive step. This graph at the bottom right depicts how the new cities added to the encoder tool using all the previously visited cities. Part 3. The attention mechanism is utilized with masking the visited cities to compute masked self-attention using the query and the unvisited cities. This queries the next city with unvisited cities, and multi-attention, residual connection, and layer normalization are used in this step. The memory and speed complexity is order of n at each recursive step. The graph at the bottom right depicts how the computed partial tool is masked, and we query the next city using the unvisited nodes. Part 4. Here, we generate the final query using attention and index sampling. A single attention is used to get a distribution over the non-visited cities. Finally, the next node IET plus 1 is sampled from the distribution using Bernoulli during training and greedy, that would be indexed with maximum probability at inference time. And the memory and speed complexity for this step would be order of n. Now, over to Anushka.
TSP can be cast as a sequence optimization problem. We have different decoding techniques, and finding exactly the optimal sequence of the nodes by exhaustive search is intractable given the O of n factorial complexity. Therefore, approximations are necessary. And the simplest approximate search is the greedy search, where at each step, the next node is the highest probability is selected, and its complexity is a linear of O of n. Better sampling techniques such as beam search or Monte Carlo tree search are known to improve results over this greedy search in TSP. Their complexity is O of Bn. Here, B is the number of beams in case of beam search, or the explored paths in case of Monte Carlo tree search. Beam search is a heuristic search algorithm that examines a graph by extending the most promising node in a limited set. Beam search constructs its search tree using breadth first search. Monte Carlo tree search is a probabilistic and heuristic-driven search algorithm. It focuses on the analysis of the most promising nodes, expanding the search tree based on random sampling of the set. The final set of nodes of each tier is then used to weigh the nodes on the tree so that the better nodes are more likely to be chosen in the future. Now, moving to analyze the numerical experiments from the paper. The results are divided into two columns. TSP 50 is where we consider 50 cities or nodes, and TSP 100 is for 100 nodes. The OBJ objective shows the total length of the path or tool. So, lower the objective, the better the result. Gap is the difference between the solution that we get and the optimal solution. In this case, we have considered the optimal solution to be Concord. Hence, the gap for Concord is 0.00%. T time means the total time for 10K TSPs in parallel, and I time means the inference time to run a single TSP in serial. So first, we can see that Concob and Gurobi are the integer programming algorithms. These are followed by the heuristic algorithms. The best heuristic algorithm is LKH3. Then we have the neural networks with greedy sampling, where we take the max probability in each decoding step. After which we have neural networks with advanced sampling by using beam search or Monte Carlo tree search. Here we can see that for TSP 50, using greedy sampling, we get a gap of 0.31%. And by using beam search, it drops the solution and it becomes very close to optimal. For TSP 100, using greedy sampling, we get a gap of 1.4%. And using beam search, it again drops, this time to 0.39%. To get an idea of the path obtained by this model, we compare the path obtained by the model versus the Concord. For first starting with TSP 50, we can observe that sometimes the neural network is even able to do slightly better than Concord. As in the first example, where the length using the neural network is 5.576, while that with Concord is 5.585. Other times it is not better, but it is doing pretty well. Now comparing TSP 100, we can see that it does not do as well as Concord, but it is doing pretty well. The path for the first example, for example, is 7.89 versus 7.77, which is pretty close. Next, comparing the complexity. The complexity is exponential for Concord and polynomial for neural networks. We see the blue line denoting the performance of neural networks versus the Concord server. The difference is quite evident as we keep increasing the number of nodes as the graphs deviate. Some of the conclusions that we can now derive from this presentation are similar to the advances in NLP and computer vision, deep learning and transformer architecture can also be used to solve combinatorial problems. The proposed model improves learned heuristics for TSP50 with a gap of 0.004% and for TSP100 with a gap of 0.39%. The results can be further improved by using better sampling techniques such as beam search and Monte Carlo tree search. It is important to keep in mind, though, that neural network solvers often offer faster inference time, which is of 0 O of n square L versus O of n power 2.5 B of n. But traditional solvers like Concord and LKHC outperform learning solvers in terms of optimality and generalization. We can use learning techniques as a leverage to improve traditional solvers like leveraging branch and bound technique. Selecting the variable to branch is critical for search efficiency and relies on human engineered heuristics such as strong branching, which is a high quality but expensive branching rule. Recent works have shown that neural networks can be successfully used to imitate expert heuristics and speed up the branch and bound computational time. Future work may focus on going beyond imitation of human-based heuristics and learning novel heuristics for faster branch and bound techniques. This topic of research will naturally expand in the coming years as combinatorial problems such as assignment, routing, planning, scheduling are used every day by companies. Finally, thanks to Xavier Besson and Thomas Lawler, the authors of the paper Transformer Network for Traveling Salesman Problem, which we have followed throughout this presentation. Thank you.